Hey everybody, so welcome to Transformations section 3.81. I'm excited to be here via Loom and also with the help of my TI Nspire calculator. Here we go. I'm going to be doing most of the work here in the upper portion, typing into the Nspire, and you can see what the effects are. And maybe you can grab your calculator and do the same thing at home. Let's take a look at two different functions. Let's take a look at the graphs, and I'm going to do that by pressing the Tab button, Tab, and then x squared. Enter. There it is. That's what we're going to call the parent function. And then I'm going to press Tab again, and then x squared plus 3. I'm getting these from actually the first line of your notes. Line number 1, it says parent f of x equals x squared, and the transform function is x squared plus 3. You notice the difference between these two. It looks like one is higher up than the other. Maybe that makes sense because of the plus 3 is different. I'm going to do Control T for a table. You can see a parabola has y values that go 1, 4, 9, 16, 25, and the transform function has all y values that are 3 units higher, 4, 7, 12, 19, 28. And I think that makes sense because the equation has a plus 3 in it. Hiding the table again, I'm going to actually do a third equation, x squared plus d. And it says create a slider for d. Yes, I want to do that. So you can see here the third function has x squared plus d, and if I press escape, then I can move left or right with my arrows, changing the value of d. When d is equal to 0, it's identical to the original parent, which is just x squared. And then if I go right, 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 and d is equal to 3, then it's on top of the transform function. When you change the value of d, then you change the height of a transform function compared to the original parent. And that's why you can say that on the first line that we're going to have a vertical shift of 3 units. It's vertical because it's moving up or down, as you can see here. It's the same shape, so we'll call that a shift. Other textbooks and other places will call it a translation, and that's fine too, but I think shift is just easier. So this is a shift. Shift and translation are used interchangeably a lot in math. If you take a look at line number 2, you might be able to guess it's the same thing. It's instead of a plus 3, it's a minus 1. And so for that reason, we can say that this is going to be a vertical shift of negative 1 units. Let's actually do that here. So d equals 0, I'm going to go left, d equals negative 1. And as you can see, it's the same shape parabola, it's just moved down 1 unit. Control T for the table, and you can see with the arrows, 0, 3, 8, 15, 24, these are all perfect squares that have been subtracted 1 because d is equal to negative 1. Okay, so that's what the slider is, d, and I'm recording my slider values right here. So let's hide the table, and let's do the next one. It looks a little different. It's going to be tab, tab, up. It's going to be similar. X squared, but you can see as opposed to being written outside of the squared, we're going to do this one on the inside. So the first thing we do before we square all of our values is we're actually going to be subtracting 4. Well, that's interesting. It's over there. The transform function is to the right. Tab, tab. I think we need a different slider name for this. Why don't we call this A? And I see the minus 4 there. I'm going to do minus A here. And it's there's a very specific reason why we chose the minus, but for right now, just note that it's x minus A. Create a slider for A, yes. I'm going to move it down a little bit so they're not on top of each other. Great. I'm going to press escape so that it's no longer boxed, but it's just blue. And now that it's blue, you see the top slider for D is black, but this slider is blue. And when it's blue, I can use my arrows to move back and forth. You can see, depending on the A value, I can change the position or change the location of this parabola. It gets shifted. And let's see, 1, 2, 3, 4. Now it's completely covering the red transform function because we have an A value of 4. So this is no longer a vertical shift, but it's a horizontal shift. And it's a shift because it's the same shape, and it's horizontal because it's moving left or right. And I often find that using left-right terminology with this kind of thing and in math in general is kind of problematic. So I'm just going to say that this is a horizontal shift of 4 units. It's in the positive 4 direction. Now, you might say, well, wait a minute, Bergman. We got x minus 4 in the original equation. Shouldn't that be a minus 4 units? And you might even expect that, like, had I asked you to guess, is this going to move the vertex from 0 to positive 4 or negative 4? When you're looking at this equation, you'd say, of course, it would move the vertex to negative 4, but it doesn't. Let's take a look at the table of values. All right, so here, when x is equal to 0 and the parent function, 0 squared is 0. And that's where the vertex is, 0, 0. But if you look at the transform function, here, the vertex occurs when x is equal to 4. 4 minus 4 is 0, squared is 0. So it takes a value of x equals 4 in order to give us a y value of 0. And perhaps that's why you can see that the whole thing gets shifted positive 4 units when we see x minus 4 squared. So we're going to say that the a value is 4 here, positive 4. And that might, like this little asterisk is here because it might be opposite of what you would expect. Control T to hide the table. Tab. The next line on your notes is line 4. It says x squared and then x squared plus 1. Let's type that in. Tab, 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 up, up. Okay, x plus 1. X plus positive 1. See where that graphs. In the negative direction, moves over 1. The vertex is over. I see in the equation, I see x plus 1, and that number is positive, but it looks like when I type in x plus 1, what we really need is x to be negative 1 in order for us to get negative 1 plus 1 squared is 0. And that's where the vertex is going to be, the lowest y value here. You can see it's symmetric about. The symmetry here is 1, 4, 0, 1, 4. The symmetry is here in the vertex negative 1, comma 0. And that might be a bit different or a bit opposite of what you expect. I'm going to call this a horizontal shift of negative 1 units. Even though in the equation I see positive 1, visually, graphically, it gets shifted negative 1 units to the left. Next, we're going to shift things a little bit. We're going to shift gears, and we're going to talk about a different kind of slider. Tab, tab, tab. Let's go. We got a new parent function. It's no longer going to be x squared. It's going to be x cubed for the next line, line 5. Okay, so in line 5 of your notes it says the parent function is x cubed, and enter. That's what it looks like. Tab, tab, tab. So, and then we want to compare that to line 5 is 2x cubed. That's what that looks like. Huh. They both have the vertices, the center of both the red and the blue graphs are at 0, 0. So nothing has been shifted exactly, but one of them has been stretched. Vertically, the red one, it looks like it's been stretched vertically like that. Like, so it's steeper. Every single part of that is steeper than the corresponding blue part. And maybe that's because you can see here, a cubic function goes 0, 1, 8, 27, 64. But if you multiply that by 2, all the y values get doubled. 0, 2, 16, 54, 128 compared to the original. So for that reason, what we're going to say here, Control T, is that this is going to be a vertical dilation by factor of 2. It's not a shift anymore. It's what we're going to call dilation. Some textbooks call it a stretch or a compression or a flip, but those are all special kinds of dilations, so we're just going to use the word dilation here. Vertical dilation by factor of 2. And I'm going to go to F3, and that's where I'm going to put my slider. Let's call it a C value. C times x raised to the 3rd power. Create a slider for C. Yes, please. I'm going to move it up with my up arrow and hit escape. You can see it's no longer boxed, but now it's blue. The other sliders are black, so I'm selecting the C slider. You can see what happens. Get it? You can see what happens when C is equal to 1, C is equal to 2, C is equal to 3. It's getting super steep. In fact, I can even edit this. And let's go as high as 10. So This is normal. Ooh. Let's make this one -10 also. -10, just so it's kind of symmetric. All right. So here's 0, 2, 4, 6, 8, 10. Boom. It goes up really high. And so apparently the C value, the number outside of the function and being multiplied, is going to control what kind of vertical dilation is. Because C is equal to 2, this has a vertical dilation by a factor of 2. All right, let's keep rolling. Line number 6 says x squared, so let's change them all again. Back to x squared, boom, tab, x squared, Okay, so we're using x squared again as the parent function. And now we're going to let g equals 1/2, c equals 1/2, the c value, you can even type it in if you can click it there, 1 divided by 2. The c value is 1/2, 0.5, and you can see that the vertical dilation is going to be by factor of 1/2. Okay, so next, let's do a new line 7. The parent function is going to be absolute value of x, F2, and then I'm going to type in the absolute value of x divided by 2. ABS is absolute value, and you can see that's where they are. It seems like the difference between absolute value of x and absolute value of x divided by 2 is like the steepness of the red and blue lines. I'm going to put a slider in here, and my slider function will be absolute value of x divided by new slider, b. Yes, I do want to create a slider for b. Okay, I got to move this thing out of the way. When I make the slider really high, it looks like it's been stretched. For purposes I'm not going to go into right now, it might be difficult to notice, especially on the absolute value, the difference between a vertical and horizontal stretch. But because it's in a different location, I'm going to say this is a horizontal dilation by a factor of 2. And as you play with the slider, you might say, Bergman, I don't know, it kind of looks like a vertical dilation to me, right? Like, look, being stretched up and down vertically. Visually, they are, I'm not going to disagree with you, they do look very much like the same thing. Like, it's impossible to really visually tell the difference between a horizontal dilation and a vertical dilation, because they look very similar. But mostly because of the location of the variable, it's inside the function and it's being x divided by b. I'm going to call this a horizontal dilation. And you can see, if you think about it, if you look at it, it does look like I'm kind of stretching and compressing the black function here, so to look either blue or red or neither. More about this later, but I'm going to keep on moving on. Line number 8, it is going to be horizontal, it is going to be dilation because there's multiplication between the 2 and the x, and it is going to be by factor of 1/2. It's a horizontal, everything is going to be half as far away from the y-axis. In line number 7, everything was twice as far away from the y-axis, going from the blue to the red. But in line number 8, everything is going to be the distance between all the points, and the y-axis is going to get cut in half. They're all going to get closer together, and that's why it's a horizontal dilation. What I wanted to do here was combine 3 transformations onto the same equation. So, parent function of square root of x. We've got a transform function of 3 times the square root of x minus 2 plus 1. There. I'm just going to hide for a second. Left arrow, left, 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 space. Space, good. Clicking on white space, there it is. You can see they kind of have this kind of a similar shape. They both start at a vertex and they go kind of upwards, but one of them is steeper than the other, and of course the red one which is steeper. It's also been shifted vertically and horizontally. And looking at the equation, we might have been able to predict that beforehand. This +1 right here is outside of the function, and there's addition, so that indicates a vertical shift of 1 unit. This times 3 over here is also outside of the function, the square root function. It's responsible for the vertical dilation by a factor of 3. And this -2 here is responsible for the horizontal shift. It's inside the function, and it has been moved 2 units, positive 2 units. And remember, because it's inside the function, we might see the x -2, but really we want to, that's actually opposite of what occurs. You can see the red function over here is moved to the right 2 units. So it's a horizontal shift of 2 units. That's opposite of what we might expect if we just visually look at this and see a minus. I'm going to see if I can do the slider. All right, so what this would be, it would be c times the square root of x minus a plus d. Okay, and then let's actually graph it. I have to go back. There it is. All right. So if we give the d value d slider a value of 1, and if we give the a slider a value of 2, and we give the c slider a value of 3, can we do that? I have to type it in. You can see that the black slider graph is directly on top of the red one, because I gave it the a equals 2, c equals 3, and d equals 1. Just to kind of sum up things, anytime you have multiplication or division, that's going to indicate a dilation. Anytime you have addition or subtraction, that's going to indicate a shift. The number is inside the parentheses or inside the function, then it's going to be a horizontal. If it's outside of the parentheses, it's going to be vertical. And this is kind of a summary of where all the values are. The a is inside minus a, b is inside with division, c is outside with multiplication, d is outside with addition. There it is. Thanks for paying attention. Thanks for taking great notes, and I'll see you in class tomorrow.